The recording is ready.
Cool. Yeah, so can everyone see my screen?
Yes. So it's ready for you now. You can start.
Ready to start now. Okay, cool. Yeah. Hi, everyone. I'm Emily, and I'm giving a tutorial about cyclic voltammetry today. So just for a bit of background, I work on the flow battery team. For some context about what we're doing is we're looking at using eutectic mixing of quinones to form high energy density redox flow battery electrolytes. So on the left here, I just have a schematic of a flow battery. Here on the left-hand side in blue, we have a quinone hydroquinone electrode. In this schematic, it's paired with hydrogen on the opposite electrode. But what's happening is we have quinones and we're forming hydroquinones as our discharge species, and that's one side of the battery. And then we can pair it with something else on the other side. In this case, it's hydrogen. But the flexibility of flow batteries allows us to have like multiple different options for what we could put on the opposite electrode. The main thing that we're focusing on, though, is the quinone electrode. So here's work done by Antonio, Davey, and Victoria, who was a master's student previously with our subgroup, was to look at eutectic mixing of quinones. So they found that when you mix different low molecular weight quinones, we can depress the melting point and make mixtures of these quinones that are liquid at lower temperatures. So ideally, this would allow us to mix together low molecular weight quinones to form a high energy dense quinone liquid, which you could use as a liquid electrode for redox flow batteries. So we're ultimately trying to build a battery. So one question might be, why are we using CV? Maybe that's not a question, I don't know. But we use a flow battery setup, and then we also use CV. So in the top picture, we have our flow cell setup that we use in the lab. So this square part here is our flow cell. So it's a compression cell. And there's like two end plates, and then there's two electrodes, and then there's a membrane in the center separating both sides of the cell. And we flow an electrolyte solution through each side of the cell. We sometimes place this in an oven. So you might have seen this kind of weird looking setup in the 184 old vacuum oven, where we've been working on some low temperature cycling experiments. And with this setup, we can like test our quinone mixtures in a flow battery configuration. But we also do experiments in the glove box with a 3 electrode setup. So that's where we do CV, and this has some advantages over the flow cell setup. So this simplified experimental setup allows us to do like quicker screening of our system. So this could be like what quinones we're looking at, what like supporting electrolytes we're pairing it with, and like different solvents that we might be using. So we can more quickly understand the compatibility of these different materials and the reversibility of the electrochemical reactions in the presence of these different solvents or supporting electrolytes. This 3 electrode setup also has fewer components. So in the flow cell, we have contributions from the membrane interface, transport through the porous electrodes. We can also have crossover between the positive and negative side of the battery. So testing in this like 3 electrode setup allows us to exclude those contributions and look more closely at what's like going on with the electrochemistry of the quinone. Also, we're able to do more like quantitative electrochemical characterization. So using CV, we can determine redox potentials for these different molecules. We can also look at diffusion constants in different like scenarios. And we can also determine rate constants and chemical reaction equilibria for like coupled chemical reactions. A lot of people in our group are probably familiar with cyclic voltammetry, so I apologize if this talk is slightly boring, but I think it'll be especially helpful for people that are newer to the group and are less familiar with cyclic voltammetry. So on the left here, I mentioned that we're working with a 3-electrode cell. So here's a quick diagram of what that is. We have a working electrode, which in our case is normally a platinum or carbon like inlaid disc electrode. So it's like a disc of platinum or carbon, and then it's inside of like an insulating like cylinder. We have a reference electrode. What reference you use is particular to what type of system you're working with. So if you're working with an aqueous system, you might use like silver chloride. For non-aqueous systems, we're working with a silver quasi-reference electrode right now. There's also different options there. And then for a counter electrode, we normally use a platinum wire. And then in your solution, you have your redox active species at some concentration, and it's dissolved in a solvent. And then you have a higher concentration of a supporting salt, which provides ionic conductivity to your solution. For CV, what we're doing is we are modulating the potential over a time period, and we're recording the current. So here we have on the x-axis time, and on the y-axis the potential. So you can see that as we increase the time, we're first increasing the potential, and then at some switching point, we reverse the potential and decrease it back to the original value. And then when we do this, we measure the current. So here's what a CV for some system where you have some species O, and then you're forming some reduced species. Your current potential plot would look something like this, where you see it peaks, and then as you reverse the potential, you get a peak in the opposite direction. This might look kind of weird. So this plot is from Barden-Faulkner, and they use a different convention for the current. So for a quick aside, I'll talk about 2 different plotting conventions that are used for cyclic voltammetry. So the one that we see here and that is used throughout Barden-Faulkner, which is a common reference material, is the American convention. So in this convention, from left to right, potential goes from high to low, and reductive currents are on like the positive y-axis, and oxidative currents are below the x-axis. Whereas for most like current papers, we use this IU-PAC convention, which makes more sense like intuitively. So as you go from right to left, the potential decreases, and then we have reductive currents below the x-axis and oxidative currents above the x-axis. So what I'm going to talk about is what dictates the current response to this applied potential, aka why do we get this duct shape? So the current potential curves for CV have this like double peak shape that is often described as a duct, which you can sort of see here. It comes from a lot of things, but mainly kinetics, thermodynamics, and mass transport all play a part in this. You might feel like SpongeBob, like you got kinetics and mass transport, and you're trying to figure out like what's happening. Could also think about it like the food pyramid of cyclic voltammetry, where we have thermodynamics, which plays a big role, and you also have to worry about kinetics, mass transport, and then if you have clean electrodes and good luck, you might get some useful data from cyclic voltammetry. So starting with thermodynamics, I'll talk about this briefly, but I'd also suggest you look at Jeff's electrochemistry tutorial from a few weeks ago, in which he discussed thermodynamics in a lot more detail than I plan to discuss here. But the main like thermodynamic equation that we want to consider when we're talking about cyclic voltammetry is the Nernst equation. So we have some formal potential for our redox reaction at standard reaction conditions. And then knowing the conditions of our system, so here we have the activity of the oxidized species over the activity of the reduced species. For species dissolved in solution, we normally use the concentration of the species. But from this, we can determine the equilibrium potential for the reaction. And this E, the potential, is what we're modulating in CV. So as we're scanning over the potential range, we're modulating the free energy of the reaction, and this has an effect on the activities or the concentrations of our oxidized and reduced species near the electrode. Secondly, we need to consider electrode kinetics. So yeah, in this diagram, this is also from Barton-Faulkner. We're looking at the reaction energy diagram for the oxidized species on the left and the reduced species on the right. So to do this electron transfer reaction, we're going through some like higher energy transition state. And we can describe this using the Butler-Volmer equation. So if we consider the reaction rates, so we have two possible reactions that are happening. We have our forward reaction going from the oxidized species to the reduced species. And then we also can consider the reverse reaction going from R to O. So our net reaction is the rate of forward reaction minus the rate of the reverse reaction. And we can relate this reaction rate to the current, which we measure at the electrode. Using this like Butler-Volmer transition state, like semi-empirical treatment, we can determine the rate constants for the forward and reverse reaction. And then using our like net current, which we described above, we can know the current for the reaction. This takes us to the Butler-Volmer equation, which we'll use to describe the current at the electrode surface. So from this equation, we can see that the current is a function of the rate constants of the reaction, also a function of the concentration of the species at the electrode surface, and also a function of the applied potential. So like we discussed before, there's a lot of factors at play in determining what the concentration will be at a given potential. The third thing that we need to consider is mass transport. And the main equation that we'll use for this is the Nernst-Planck equation. So the Nernst-Planck equation has three components to describe the three different modes of mass transport. So we can relate the flux of some species I to the diffusion. So that's related to the concentration gradient. And then we have the migration component, which is related to the potential gradient. And then we have the convection component if we happen to be like stirring our solution in any way. Looking again at the three electrode system, which we described before, normally cyclic voltammetry is done in a quiescent solution, which is like just a jargon word that means it's an unstirred, like still solution. So this allows us to neglect the convection term in the Nernst-Planck equation. Also, you typically have a high concentration of supporting electrolyte. So this allows us to neglect the migration term. And as a result, we're just left with this first term where our mass transport and the flux of the species I is dominated by this diffusion term, which comes from the concentration gradient in solution. So from the Nernst-Planck equation, once we get rid of the migration and convection terms, we're basically left with fixed first law, which describes the flux related to the concentration gradient. This equation like doesn't account for time at all. It's like a steady state equation. But then if we consider fixed second law, which we get to by using fixed first law and considering conservation of mass, Then we can consider how the concentration changes with time as a function of the concentration. So here, we'll first look at this picture in the top right. So to understand the coordinate system for this, we have our electrode here, and we're considering like just a unidirectional case. So we have our electrode, and at the electrode surface, x equals 0. And then far away from the electrode surface, at x equals infinity, we have some bulk concentration of our oxidized species, which we start with, and that's going to be CO star. So looking at our initial and boundary conditions, first we have our initial condition. So at time 0, everywhere in the solution, the concentration is CO star. Then the second two equations are our boundary conditions. So as x approaches infinity, the concentration at all positions, the concentration as x approaches infinity at all times is going to be CO star. And then our second boundary condition is that at the electrode surface at all times, the concentration equals 0. So that's the particular case that we're looking at here, where you're using up all of your reactant at the electrode surface, so the concentration is 0. When we apply these initial and boundary conditions to Fick's second law, which is the diffusion equation, we get the concentration of our species as a function of position and time. Looking back at Fick's first law, we can say that the flux at the electrode surface is related to the current, and this is a function of the concentration gradient, again, like we saw before. And now that we have the concentration as a function of potential and time, we can use this in Fick's first law, and we arrive at the Cottrell equation. So this describes the current as a function of time. This equation you've probably seen before for chronoamperometry. So if we apply a potential step, we can look at the concentration change over time, and the current will follow a t to the minus 1/2 function. It's important to note that the Cottrell equation only applies for unidirectional diffusion. So in this example, we were considering like just diffusion in the x direction. But this is valid for like a case where you have like a planar electrode. Yeah, and this equation is useful for chronoamperometry, and it can also be used to look at CV after like the peak. The final part of the CV pyramid is the experimental parameters. So there's a lot of different experimental parameters that you can control in cyclic voltammetry, but then also in like 3 electrode cells in general. So one really important is the reference electrode. I mentioned previously that there's different reference electrodes that you would want to use for different systems. So that's important because you want your reference to be at a constant potential so that you have like a stable reference and it's not drifting during the experiment, because that would affect your results. You can also use working electrodes of different materials. You can use different solvents, different supporting salts, and these will also have impacts on the voltammetry that you see. You can also use different analyte concentrations. The factors that you might want to change in a CV experiment would be scan rate, so how fast we're sweeping the potential, the potential sweep window, so like the range that we're starting from and then reversing from. And then you can also repeat like any number of cycles, and you might want to do this for different reasons in your experiment. So if we put all these together, we can look at what the current potential like function looks like for a CV experiment. So there's a few different things which I'd like to point out on this plot. So first, we have the two different peaks. So we have the cathodic peak, which is at C, and then we also have the anodic peak. So these peak heights are one thing that you might want to measure. We also have this E1/2, which is the half wave potential, and that's going to be like the redox potential for your reaction. And then another factor that you might want to look at for CV is the distance between these two different peaks. So like the delta E between the anodic peak and a cathodic peak. The delta E can tell you something about like the ohmic resistance you have in your system. It could also tell you about like the kinetics of your system, like if it's like Nernstian and like highly reversible, or if like the peaks are further apart, then you might have a quasi-reversible or possibly irreversible electrode reaction. So now that we went through the diffusion equation and looked at the concentration profile, we can look at the like how the concentration profile aligns with this like current shape, just to like put it all together. So at A, at the start of your experiment, this blue line is the concentration of our reactant, and you can see that everywhere the concentration of the reactant is 1, and we don't have any of our reduced species. And then at B, as we reach this E to the 1/2 potential, our species are in equilibrium. So we have an equal concentration of the oxidized and reduced species at the electrode surface. Then as we get to C, we're starting to deplete the reactant, and this is where the CV peaks. And then once we get to D, we've fully depleted the concentration of the ferrocenium species at the surface. And so this region is in like diffusional control, like we just looked at with the Cottrell equation. So then after we reverse the potential and we scan to E, we're in a similar case as we were at B. So we again have an equal concentration of the oxidized and reduced species at the electrode surface, but our bulk concentration is still that the oxidized species is at a concentration of 1. So that's why we have a different shape than we do in B. But then as we continue, we see sort of the same thing that we saw on like the forward scan, where now we're depleting the concentration of this reactant species. And then as we get back to the starting potential, our concentration profile looks similar to how it looked at A. So that was an example for ferrocene. So ferrocene is a highly reversible like system that's often used as a model, but in practice, the CVs that you may see in the lab don't always look as perfect as that one. So first we have what you might see for like a reversible like Nernstian reaction. So that would be something like ferrocene. And then if we have a quasi-reversible reaction, so in a quasi-reversible reaction, the rate constants are slower. So we do see some impact of the kinetics, and the delta E here is a lot larger. For an irreversible system, here we see like a really irreversible system where we only have a peak in one direction. So we're able to form the oxidized species, but then we're not able to go back and reduce it. So there's no like reverse peak on the reverse of this scan. So that would indicate that you have a reaction that's irreversible. There's some additional considerations that you might also want to consider. So one other thing is the charging current. So there's some like background current that is due to capacitance. You might want to take like a blank measurement of your solvent and salt without adding your redox active species to determine like the capacitive like background current. Another thing to note is the solution resistance. So when you add salt to the solution, you have some ionic conductivity, but if the ionic conductivity is low, then you could still have a lot of solution resistance. In this figure here, we can see that the working electrode is at some potential, and then your auxiliary or counter electrode is at some other potential, and this IR drop is due to the solution resistance. But the potential that you're measuring at the working electrode is the potential between the working electrode and the reference electrode. So this potential drop here is an uncompensated resistance. So if you are able to move your reference electrode closer to your working electrode, then you're able to reduce this uncompensated resistance that might distort your voltammogram. Also, we only considered a one electron reaction without any coupled chemical reactions. So you could also see different things with more complicated kinetic systems. So for example, if you have consecutive electron transfer reactions, or if you have coupled chemical reactions, then this will make your voltammograms look different. For an example of this, first we have on top an example of a reversible electrochemical reaction, so that's ER, and then an irreversible chemical reaction. So as we go from the red curve to the blue curve, that's with increasing scan rate. So at slow scan rates, you're able to do your forward reaction, but then some irreversible chemical reaction results in you not being able to do the reverse reaction of the electrochemical reaction. If you scan really fast, then you might be able to do the reverse reaction of your electrochemical reaction faster than this irreversible chemical reaction can occur. So it's important to do CVs at different scan rates so you can try to like tease out what mechanism is at play. Next is an example of a reversible chemical reaction followed by a reversible electrochemical reaction. So here you're going from blue to red, we're increasing the forward rate constant for the chemical reaction. So if the chemical reaction is highly reversible, or sorry, if the chemical reaction has a faster rate constant, then this first peak is higher. Again, you can see that the peak changes with scan rate. And then lastly, we have an example of two consecutive electron transfers. So then in this case, the difference is we're changing the separation between the peaks. So in the red line, this is the case where the two electron transfer reactions have potentials that are pretty far away. But then as we go to this blue curve, this is still a plot for like two consecutive electron transfers, but the potential of the second transfer is negative to the potential of the first transfer. So it actually merges together to form like one peak. One other thing I just wanted to point out is that if we look at like the blue curve from this top plot, and then the red curve from the center, and then again, look at like the blue curve from the bottom, all three of those voltammograms look pretty similar. So you could get a voltammogram that could be representative of a bunch of different mechanisms. So it's important to make sure that you do your experiments at different scan rates, and like change other things in the experiment to make sure that you are attributing the correct mechanism to your voltammetry that you're seeing. Yeah, so that's what Patrick's doing here. He's like taking a close look at his CV results to make sure that he's not like ascribing the wrong mechanism to the CV. Another theoretical treatment that can be used is the Reynolds-Sevick analysis. So I'm not going to walk through the derivation at all, but this is an equation that is used to determine diffusion constants. So this equation relates the peak current as a function of scan rate. So if you do a CV at multiple scan rates, you can plot the peak current versus the scan rate to the 1/2. And by looking at the slope of that line, all the other things in this equation are constant. So we have the number of electrons transferred, Faraday's constant, area of your electrode, your bulk concentration. The only other constant that we don't know is the diffusion constant. So by doing this, you're able to determine the diffusion constant for different molecules. So another concept in cyclic voltammetry is systems that will give you steady state mass transport. So Alan talked about one of these last week when he discussed RDE. So one like class of these methods is hydrodynamic methods. So this includes the rotating disc electrode, where you're spinning this electrode and you're like hydrodynamically controlling the mass transport by modulating the rotation rate. Another example is the flow channel electrode. So here the electrode is this like band, and you're modulating the mass transport here by flowing at different flow velocities. A second case of a type of experiment that gives you steady state mass transport is looking at ultramicro electrodes. So we previously discussed the case of planar electrodes that have like semi-infinite linear diffusion. So those are like larger electrodes. Ultramicro electrodes are really small. Here in this paper, you see that the dimensions of the like active surface of the electrode are like very small. This one is like about 1 micron. So when you have an electrode that's this small, you get a different diffusion profile, which allows us to obtain a steady state mass transport similar to what we see with a rotating disc electrode. So in this plot on the left, in the first column, we see what we would see if we have a large planar electrode. So this would be semi-infinite linear diffusion. We get this like duct-shaped curve like we've just walked through in the previous section. As we decrease the size of the electrode, we're going from this planar semi-infinite linear diffusion to a radially convergent diffusion once our electrode gets really small. So instead of seeing these peaks, we just see like a steady state like sigmoidal curve. The main difference here between the planar electrode and the ultramicro electrode is the relationship between the thickness of the diffusion layer and the electrode size. So in an ultramicro electrode, we develop a really thick diffusion layer relative to the electrode size. So this allows us to get into a steady state regime where the mass transport is completely controlled by this radially convergent diffusion. A couple of reasons to, or like cases where you would want to use ultramicro electrodes is first, in cases where you might have low ionic conductivity, you might have no supporting salt, or you might not have a solvent. And this is because ultramicro electrodes allow you to have a really low IR drop. So since the current we're measuring at an ultramicro electrode is really small. The size of these electrodes is on the order of like microns. So we get a very small current. This allows the ohmic drop due to the uncompensated resistance to be quite small. Also, we're able to scan at fast scan rates that are not typically accessible with like larger like planar electrodes. So how fast of a scan you can do in a CV is related to the cell time constant, which is the uncompensated resistance times the capacitance. So this is a function of the electrode radius. So if our electrode radius is really small, then this gives us a lower cell time constant. So since our cell time constant is smaller, then we're able to scan at faster scan rates. So thinking about these like steady state mass transport methods, we can again look at Fick's first law, which we talked about before, where the flux of a species is related to the concentration gradient at the electrode surface at x equals 0. So if we're talking about a mass transport limiting case, we again want to say that the concentration is 0 at the electrode surface. So our concentration gradient will be the bulk concentration minus the concentration at the electrode surface over this delta, where delta is our diffusion layer thickness. So that's like this region here where we're going from the bulk concentration to the electrode surface. The thickness of the diffusion layer is not super well known, so it's often described in terms of a mass transport coefficient, which is the diffusion constant divided by the Nernst boundary layer thickness. If we input that this concentration is equal to 0 at the electrode surface, and then we plug in MO for this diffusion divided by the Nernst boundary layer, and then we know that the flux is equal to the current divided by N times F times the area of the electrode, we can get a steady state mass transport limiting current, which is a function of the bulk concentration and the mass transport coefficient. And the mass transport coefficient has different functional forms depending on what type of electrode you're using. So for a disk ultramicroelectrode, it's a function of the diffusion constant and the electrode radius. For the rotating disk electrode, this equation might look familiar from Alan's talk last week. This functional form here is found in the Levitch equation. But for the mass transport at an RDE, it's a function of the diffusion constant and the rotation rate, as well as the kinematic viscosity of your solution. Just like a quick aside, I'll go through this really fast since we're close to the end of time. But it could be interesting to compare the mass transport coefficients for an ultramicroelectrode versus a rotating disk electrode. So if we consider a solution of ferrocene in a 0.1 molar salt solution in acetonitrile, we know some diffusion constant for ferrocene on the order of 10 to the negative 9 meters squared per second. And we have some kinematic viscosity for the acetonitrile salt solution. For a 5 micron radius RDE, we can calculate the mass transport coefficient. And we get this value here, which is like about 6 times 10 to the negative 4 meters per second. If we wanted to have the same mass transport coefficient at an RDE, it could be interesting to know how fast we would have to rotate to have that same mass transport coefficient. So from the previous slide, we know that the mass transport coefficient at an RDE is again related to this kinematic viscosity, the rotation rate, and the diffusion constant. So using the the values that we have for the system, and then setting it equal to the mass transport coefficient for the ultramicroelectrode, we can then solve for the rotation rate that would give us like an equal mass transport coefficient. Interestingly, it's super high. So to achieve the same mass transport coefficient, you would need a rotation rate of almost 23,000 RPM. So that's like considerably higher than the normal rotation rates that people use for RDE experiments. Just another quick aside, all of the equations that we considered here have been derived for dilute solutions. So since we're looking at systems of like liquid quinones that are highly concentrated, these like don't quite fit the equations, and there are some other things that we need to consider. So in this paper, this group looked at a redox active organic liquid for cyanopyridine and found some other like non-ideal scenarios that happen when you're doing voltammetry in a like extremely concentrated liquid. So this liquid was almost 10 molar. And they found that different things like the solution resistance and the fluid convection are dependent on the current. And you can also have different factors which are normally considered constants that are then dependent on the concentration of your oxidized and reduced species. In this talk, I used a number of different references. I included them here. I think these are 3 really good resources to learn more about cyclic voltammetry, especially if you're new to electrochemistry. Electrochemical Methods by Bard and Faulkner is like a classic. And then this Understanding Voltammetry book is also really good. And then A Practical Beginner's Guide to Cyclic Voltammetry is like a pretty quick paper that goes through some like experimental considerations that you should make when doing cyclic voltammetry experiments. So that's it. Thanks to everyone in the group, and then thanks to Old Reliable, aka Bard and Faulkner. I'll take any questions.
Great, thank you, Emily, for your talk on CV. Like Emily said, if you have any questions, please feel free to unmute yourself and ask your questions.
I have a quick question about the mass transport part of this interpretation of the CV. I've been thinking about this a lot since we've been fighting with reviewers, arguing about like diffusion limitation in battery materials. And I often see like this argument where they do CV on like a porous electrode and then attribute the trailing tail to mass transport phenomena. They think if you're in a reaction limited regime, then even without mass transport, just the depletion of your reactants can result in a similar, qualitatively similar feature. And that made me think like, I mean, the main difference seems that like instead of having a uniform progression of your reaction spatially, instead if you have like a sort of like a particle by particle type of progression, then many of these very basic equations might break down, I feel. So I wonder how this is addressed in the more typical setup of electrochemistry.
Yeah, that was a lot, so I'm not 100% sure what your question was, but I agree with you that, especially if you're considering a porous electrode, I think that's definitely where these equations would start to break down, because like we're just considering like semi-infinite linear diffusion in like the regular equations for CV, and the diffusion through a porous electrode is going to be already pretty different than that.
I guess, yeah, another way to maybe ask the question is, let's say you have like a planar, like thin film, where you might initially assume that semi-infinite diffusion is like a valid setup. But then experimentally, how would you confirm that you're in a mass transport limited regime where you can use all the standard equations? If, for example, if part of the thin film reacts first and then completes the reaction before other parts of the film start reacting, then I think like the end of the CV, where the trailing tail might look like diffusion, like mass transport limited, but actually just come from the depletion of your total active area. So I'm wondering if there's a way to experimentally distinguish these two scenarios.
Yeah, one thing that I've seen to like look at differences between diffusion limited regime and like if you're diffusion limited or kinetic limited, one thing that I saw was doing like a potential step experiment, which I guess like ends up being similar to CV, but like you could separately analyze like what's happening at like each potential step. I don't have like a super like rigorous answer, but I would think that if you did like a more controlled step experiment, then you might be able to look at each of the individual steps, and it might have like a different relationship if you have like a kinetically limited regime versus if you had like a purely diffusional regime.
So maybe you're looking at the temporal evolution there.
Yeah, or could you do something to like control the mass transport? So then like you know how you're changing the mass transport, and then if like that's known, then you could more easily like look at the kinetics, because you then like that would be something that's changing and you don't know how it's changing.
And then maybe if you can rotate your electrode inside a coin cell.
I have
or something.
A quick comment, because Stephen, like the way you were asking the question, I'm not sure if I interpreted it correctly, but it sounds like, you know, you're thinking of like the battery material where part of the surface can like stop reacting because it's full of lithium. And then like
like if some of the particles are, if you think of it as a particle ensemble, then if some of the particles finish the reaction, then you're decreasing the.
Right. But I guess like in like the standard CV, if you just have like a platinum electrode that's not reacting, then it might be very different, because I think in that case, like if the current is going down, I feel like it has to be some sort of mass transport, basically. Like you're just not getting enough reactants to the surface, essentially. Like
Right.
not like the platinum will stop being, you know, having the reaction happen at a certain point spatially.
Right. So it's a fairly different system in that sense.
Also, I don't know if your system is like spatially resolved at all. Like when you said some particles have completed the reaction, but some particles haven't. Because there's also electrochemical techniques where like, I think it's called scanning electrochemical cell microscopy, where you can like do it in like do your electrochemistry in like a small volume and like one part of the sample, and like spatially resolve the electrochemistry that way.
Once there's some way to get information about the spatial distribution, I think it gets a lot easier. I was just wondering, because before you have that information, we do these macro measurements first and then imagine what's going on without really seeing what's happening. Yeah, that's basically, that was a question I was thinking about. But definitely if there's microscopic information, it helps.
Emily, I had a really quick question, very opposite of Stephen's. When you connect the biologic potentiostats to your electrochemical cell, which convention is the biologic using? The American one or the IUPAC one?
The way that the plotting software that the biologic uses is in the IUPAC convention.
Okay.
Yeah.
Cool. Because I always forget when I'm connecting the electrodes, like which one needs to go to like which part. So good to know.
Are there any questions? If not, we'll conclude our tutorial session for today. And thank you, Emily and Shin, for your talk. I think Swati and Peter